Hello physical science student, welcome to the next series of videos. This is going to be on chemical reactions, and looking at your textbook it's pretty much based on chapter 11. So if you want some supplementary reading or to find where most of the questions are coming from, have a look at chapter 11 in your textbook. Let's get started. First one is chemical equations. Now in this section, or in these series of videos, we'll look at the products of chemical reaction when given the reactants. So we'll be able to, if given the reactants, be able to work out what should occur and what we should have as the products. And we'll get better at that during the course of the year as we learn more. Remember, this is just the start, a bit of an introduction to it. We'll also learn that there's different types of chemical reactions. There's combination, decomposition, replacement and combustion. And these are terms chemists use, but we sort of group them into different groups depending on what sort of chemicals are actually involved. But just be mindful of those, and I'll point out a few as we go, just so you're aware of that terminology. We'll be able to balance chemical equations, which is a very important skill, a very basic one that you need to get your head around with a bit of practice. Now, when chemical changes take place, we may observe one or more of the following. Now, you've probably observed chemical reactions already, and you may have already seen some of these. So let's just go through them. A substance disappears. So, like evidence of a chemical reaction, you pour a powder into a beaker of water, stir it around, it disappears. That's a chemical reaction. A gas is given off. So if you see bubbles, if you see what's called effervescence, that's a result of a chemical change occurring, and so we could write the reaction about that. A solid is precipitated. So precipitation is the formation of a new substance that is only slightly soluble and settles as a solid. And we'll do a prac on precipitation where you'll get to see lots of precipitation reactions. Basically, you get a solid where there was no solid before. So you might have two liquids which are completely clear, pour them together and they're no longer clear, they're cloudy, or a solid actually sinks out to the bottom. A colour change takes place. That's evidence of a chemical reaction. A temperature change occurs. So sometimes when we're doing chemical reactions, you should just gently touch the test tube to your hand, and you might find that some of the reactions produce heat. Other reactions are actually, the test tube will be cold, and that's what chemists call exothermic or endothermic, but we don't need to know that. You'll learn that in Year 12 chemistry if you do it. A new odor is released, so you get a smell that wasn't there before. Light is given off. This is a reaction you don't really see in physical science classes, but if you've ever been to a disco or where you've had glow sticks, or some when you go boating, some people use chemical lights, little plastic tubes, and you crack them, or you crack a little vessel inside and mix the chemicals together, and they give off light. They're also used in caving because they give off light, but they don't give off any fumes or anything. And therefore they're safe in a confined environment like a cave. Now, chemical equations, just to get your head around what we mean by a chemical equation, here's a definition straight out of your textbook. Chemical equation is a way of summarizing. So it tells us the chemist can read a chemical equation and get a lot more information out of it than what would be hinted at by just the letters and symbols. So it's a way of encoding lots more information, and you'll get practiced at this. And so when we give you a chemical equation, you'll be able to work out what the reactants are, what the products are, what the states of the various products are, what's happening, and what type of reaction it is. So let's have a look at some of those. Now, in chemical equations, we usually put the reactants on the left hand side and the products on the right hand side. And for physical science, we pretty much put an arrow going from reactants to products. When you do more chemistry, you'll get this arrow will actually be replaced with a double-ended arrow, because reactions can actually go both ways usually, and we as chemists, you would define which way the reaction's going by the conditions that it's in. But for us, we pretty much just go from reactants to products. Now this is an example. Here you have, now hopefully all these letters mean something to you because you've remembered your elements on the periodic table. And so here we have sodium, and we're reacting it with Cl2. Now that's chlorine gas. The 2 tells us it's a gas because it's 2 chlorines joined together. They're our reactants, and it's producing something that we would call sodium chloride. And we'll learn why this is sodium chloride and not sodium chlorine when we do ionic substances. But this is sodium chloride, and this is the product. And it is an example of a combination reaction where you're combining things together to get something new. Now, this doesn't tell us anything about the states, and you would also notice that there's one sodium here and one sodium here, which is fine, but there's 2 chlorines here and 1 chlorines there. And now, chemists are not God. They cannot create or destroy atoms, and therefore we need to make sure equations balance. And down here we've got the next version of the equation, which is giving us a lot more detail. First of all, you see these things in brackets. These are the states of the various substances, and so the S tells us it's solid sodium, the G tells us it's gaseous chlorine gas, and the product is a solid. Now notice also the 2 here. Now this 2 is a coefficient that's used to balance. Just as this 2 down here tells us there's 2 chlorines joined together, this 2 here tells us there's 2 sodiums. It's like in maths where you have a 2 multiplied by something. There's a little invisible multiplication there, and if you look over here, this little thing actually, if we were to do it in maths, we would write 2 bracket NaCl, okay, because it's actually 2 times everything, or another way of writing it is 2 times NaCl. Now why do I say that? Because sometimes students want to say that this 2 here is only 2 times the sodium, because that's what I said over here, and that's true over here, but here it's 2 times everything that follows in the formula. This one is just 2 times Na. Okay, forgetting about the subscripts. The subscripts just tell us the states. So this tells us there's 2 sodiums and 2 chlorines, because if we added that up, basically we're getting 2 sodium chlorides. Now that's important because here we had the 2 chlorines. Now here we've got 2 chlorines. We've just written them differently, and that balances. Here we've got 2 sodiums. Here we've got 2 sodiums. Let's get rid of that. Now that's a balanced equation, and we'll get a lot of practice at balancing that, and you'll get more clues as to how to work these out. Next, now the states, S is solid. Now the one that's not shown there is liquid. Sometimes we get a liquid produced, and another one that's not shown is AQ, which means a solution of water, so something is dissolved in water. Aqueous, that stands for. Now here's another equation that uses a couple of other things. It's a balanced equation, and we've got the reactant on this side. In this case there's only one reactant, and we're getting 2 products. This is an example of a decomposition reaction, in that here we've got what's this, hydrogen peroxide, H2O2. It's in solution with water, okay, and it reacts to form water and oxygen gas, which is O2. Now this little guy here, which is magnesium oxide, it's referred to as a catalyst. And what a catalyst does is it's something that assists in the reaction occurring and aids the reaction to actually occur faster, but doesn't get consumed in the reaction. So it sits up here above the arrow because it's not actually involved in the reaction. It just assists the reaction occur. And there's a whole branch of chemistry related to finding catalysts that can actually speed up processes and make them more efficient. And so this is an example of one, but we don't really need to know anything more than that. Notice that this is also balances. If we quickly, this is a little crash course in balancing. Remember, we're going to look at balancing a lot more. Here we've got a 2, so effectively in mathematics that's a 2 times, now there's no bracket here, but there's a hidden bracket, 2 times O2. So if I asked you how many hydrogens you have in here, I hope you would say you have 4 hydrogens. And if I asked you how many oxygens you have, hopefully you would say 4 oxygens. And that means that on this side we've got 4 hydrogens and 4 oxygens. We need 4 hydrogens and 4 oxygens on this side. And if we look here, 2 times 2 hydrogens, so this is 2 times H2O, so that would be 4 hydrogens, and we have 2 oxygens there, and then we've got O2, which is also 2 oxygens, so these guys combine to give us 4 oxygens, and therefore it balances. And we'll learn how to do that. Let's get rid of that and let's move on back to our chemical equations. Here's another one, a bit more complicated, a little bit different. Boy, we're swamping you with new stuff today. But hopefully all this will make sense to you shortly. Here we've got another decomposition reaction, and in this case it's copper sulfate solid being mixed with water. Okay, it's not a catalyst this time, we're mixing it with water. How do we know we're mixing it with water? Because now we've got AQ. We've got the copper in solution and the sulfate in solution. This is called sulfate, and you'll learn about that too. There's a lot of learning ahead of you. Now AQ means it's in solution, so we don't draw the water anymore. Now generally speaking, when I usually write these, and most chemists do, we don't bother putting the water there, because this tells us what's actually happening. The AQ, as soon as you say AQ, means there's water. And so what we've done is we've put the copper sulfate into water, and this is called a dissociation reaction, or let's get my piece of paper, a decomposition reaction. And so you're breaking something apart and giving something else. Now this balances, and I won't go through it again, but notice here you've got charge. And when we do ionic equations, you're going to learn why and how to put these charges here. Notice, just a quick little clue, is 2 plus minus 2 equals 0. So effectively the charge on this side is 0, and there's no charge shown on this side, so it's 0 as well. Charge is balanced. There's a clue. Right, let's move on. So dissociation of ionic solid is the full term for that equation. And here we're having just a change of state. We're going from water solid, which would be ice, adding heat, and that could be just room temperature, or we could be putting a blowtorch to it, and we're producing water liquid, and that's the equation for it. Now in your textbook in chapter 11 you've got all these symbols. Sometimes we put heat there. Now another way of putting heat, sometimes chemists just put a little triangle there, and then this would be a indicator, a catalyst, sorry. Yep. So we've been introduced to most of those, and we're going to use them a lot, but you can find that in your textbook. Right, let's translate chemical equations into words. So now here we have, when solid mercury 2 sulfide is heated in air, molten mercury and gaseous sulfur dioxide are produced. Write an equation for this chemical change. So the things that we've got to work out are what the reactants are, and we've got to work out what the products are. Alright, let's look at the reactants. When solid mercury 2 sulfide is heated, so that's a before type statement, so that's before, in air. Now when we say air, what we're interested in air 99.9% of the time is the oxygen. Now oxygen has the formula O2. Then we're told, let's go blue actually, So here we've got two reactants. Molten mercury and gaseous sulfur dioxide are produced. So there's a product and there's a product. Now we also have the states, and the state there is solid. Now air will be, of course, a gas, and molten, that's a liquid, and gaseous, that's a gas. So this word gives us all the stuff we need, and this is what it's saying here. Let's put it all together. Bit confusing, but that's what we end up with. And this is an example of a decomposition reaction. Let's draw some lines here. So the mercury sulfide, this guy, that's that. The oxygen, there. Molten mercury, there. Sulfur dioxide, there. And we've got the states right. Now, how did we get the formula HGS from this? Well, you're not expected to know how to do that just yet. We'll learn when we actually do ionics and covalence and metallics. And so by the end of this term, or maybe next term, you'll be able to read this yourself and put all of it into chemical formulas, because you'll know what the little tricks are to that. Initially it will start out quite confusing for you. Right, translating chemical equation into words. Another example. Write a sentence that completely describes the following reaction. And this is a combination reaction. We've got N2O3 plus water goes to 2HNO3. Now there's a little bit of knowledge required before you can do this, and it sort of starts out, the book sort of starts out a little bit confusing for you. There's a bit of expectation that you already know something. Now this would be referred to as a covalent substance because it's two nonmetals joined together. And so the way that we name nonmetals is a little bit different from how we name ionic substances, and we'll do that when we do the specific bonding types. But this would be, when we have covalence, we use prefixes to tell us the numbers. So we would say dinitrogen, the di tells us the 2 trioxide. And you wouldn't be expected to know that now, but you will be once we've done covalence. And that's, of course, water. And this, again, this is something that you won't recognize now, or you might if you've done a little bit of chemistry. But by the end of the year you will. And this is nitric acid. Okay, so basically we're mixing gaseous dinitrogen trioxide with water to produce nitric acid. They say it a little bit differently. Let's have a look at it. Gaseous dinitrogen trioxide reacts with water to produce a solution, because it's AQ, of nitrous acid or nitric acid. Right, so what I want you to have a go at doing is, don't do it right now, wait until you get into class so I can help you. Have a go at, and we'll do these questions in class, but just as a forewarning, so you don't have to ask me in class, a couple of things. There's a couple of formulas that this sort of books just expects you to know magically, but we haven't done them. And so the formula for aluminium oxide is Al2O3. The formula for potassium chlorate is KClO3, and then potassium chloride is KCl. And the rest is given to you, so you should be able to work out those questions in class. Again, just yell out if you need help. And there's the answers which will appear. Now in the next video we're going to actually learn how to balance those chemical equations, which will be fun. Cheerio.